Question that asks the average rate of change of f of x on the interval between 0 and 10 pi thirds. So the average rate of change, that is basically the rate of change between 2 points. And so we want to look at the point of f of 0 and see what that value is. So if we plug in 0 wherever we see an x in this function f of x, we get this is equal to sine of 0. So sine of 0, hopefully you guys know that by now. That one is 0. And so we have a point at 0, 0. And so we also want to look at what is the value at 10 pi thirds. So f of 10 pi thirds, we're going to go in and we're going to plug in 10 pi thirds wherever we see an x. So we have sine, we have an x there, all over 2. And replace, put in 10 pi thirds in that. We have a fraction within a fraction, and so we can deal with this by invert multiplying the denominator. We can think of that as 2 over 1. So flipping it up, we get sine of 10 pi thirds times 1/2. I'm going to reduce this a little bit. 2 goes into 10 5 times. And so this is sine of 5 pi thirds. Okay, so pi thirds, 5 pi thirds. Well, I know that this is a multiple of pi thirds. Pi thirds is 60 degrees, right? And so, but 5 pi thirds, oops, we have 5 of those. So that's 300 degrees. And so that will get me into the 4th quadrant. I need a pi thirds to get up, figure out what my reference angle is. But sine in the 4th quadrant is negative. So this is going to be equal to the negative of sine of pi thirds. Sine of pi thirds that one is root 3 over 2. So we also have a point at 10 pi thirds, our x value, and our y value is negative root 3 over 2. So the average rate of change this is equal to the change in your y value all over the change in your x value. So I'm kind of just doing notation of change of y, change of x that you're going to start seeing in this course, but also when you get into calculus. All that is this is basically your slope. So you're looking at the change in your y value all over the change in your x value. And so if we look at y sub 2 minus y sub 1, all over x sub 2 minus x sub 1. So if I look at negative root 3 over 2 minus my y value of my other point, 0, all over 10 pi thirds minus my x value of the other point is 0. Not very pretty, but we can handle it. So let's rewrite it as negative root 3 over 2 times the reciprocal of 10 pi thirds. So flipping it, we get 3 divided by 10 pi. So this should be -3 root 3 all over 2 times 10 is 20. So questions? Okay, so we were having some technical difficulties, so we went to a try it. And so if you're watching this video, you could always stop and try doing these. Stop the video and try to do these, and then restart the video. So we're going to graph f of x equals 2 times cosine of x over 2. And so there's a couple things that we did when we were graphing these. We wanted to find what the period was, and we wanted to find the amplitude, and those were very helpful to graph. And so the amplitude was the coefficient in front of the cosine or the sine function, your trigonometric function. Only cosine or sine actually have amplitude. And so our amplitude is the absolute value of the number in front. So for problem 1, our amplitude is equal to 2. So we know we have a max at 2 because we're not shifting this graph up or down. We don't have plus or minus some constant outside. So we have a max at 2 and a min, and y value we're going to hit is -2. Our period, that's where we took our argument, what we were taking our trig function of. So in this case, x over 2. And we sandwiched it in between a normal period for that trig function. And so for cosine, a normal period is between 0 and 2 pi. And then we solve for x for this compound inequality. And so we want to get rid of the x divided by 2, so we could multiply everything through by 2 to get rid of x. So 2 times 0 is 0, is less than or equal to 2 times x over 2 is x, is less than or equal to 2 times 2 pi, which is 4 pi. So once we found our period, we knew where we could start one cycle of that period and where we could end one cycle of a period. Because it just keeps repeating itself in that length. That's the length of how long it takes to repeat itself. So starting at 0, ending at 4 pi, and then we looked at the halfway value, the quarter wave value, and the 3/4 wave value. So halfway between 0 and 4 pi would give us 2 pi. Halfway between 0 and 2 pi is pi, and halfway between 2 pi and 4 pi is 3 pi. And once we found our amplitude, our period, we graphed our special values. So 0, pi, 2 pi, 3 pi, and 4 pi. Graph where your max is, where your min values are on the x or on the y-axis. And depending on which trig function we're using, depends on, are we going to start at the origin or that midway line, or are we going to start at a max or min value? Because we're dealing with cosine, we are starting at 2. And it was positive, that's why it's the max. If this had been -2, that's a reflection across the x-axis, and we would have started at the minimum value, -2. And so once you plot that, then we're going to hit our midway line, in this case the x-axis, go all the way down to the minimum value, go back up to the x-axis, and then our max value. So any questions on that? Is that helpful? Okay, so let's look at the other one that you guys were supposed to try if you had a chance. Oh well, it didn't work. We have negative sine of pi force x plus or minus 1 plus 1. Okay, so again, we want to find max, or we want to find the amplitude, which will help us find the max and the min. Amplitude, again, is the absolute value of A, which is the number in front of sine. So absolute value of -1 is 1. I noticed, though, that we have this +1 outside, and so this tells us that we're going to shift the graph up vertically 1. So shift that. Y equals negative sine of pi force x up 1 unit. That's shifting things up 1, where my normal max would have been 1. Well, if I shift my max of 1 up 1, now my max is going to equal, is that 2? My min, well, my negative sine of pi force x, the min was at -1, but if I shift up the min from -1 up 1, my min is going to be at 0. And we have a midway line. So the x-axis, if we treat where things were crossing, is at that midway line. The midway line is at y equals a little bit. We're shifting everything up 1 and it's I'm going to put a dotted line, and we're going to treat that like it was the x-axis on the original. And then that was at 1, so 2. Oops, that's not 2, that's 3. So we also need to figure out what the period is. And so the period is between 0, pi force over x, is less than or equal to 2 pi. So if we multiply everything through by 4, actually let's just multiply everything through by the reciprocal of what's in front of x, which is 4 divided by 5. So 4 over pi times 0 gives us 0. Is less than or equal to x, which is less than or equal to. Well, notice when we distribute over here, our pi's cancel, and we'll be left with 4 times 2, which is 8. So we have a start value at 0, an end value at 2 pi, no, at 8, I'm sorry. Halfway value is 4, quarter between 0 and 4 is 2, half between 4 and 8 is 6, so 3/4 is 6. So put those points on your graph. And then we need to determine where we're going to start our trig function. So we're a sine function, so that's normally at the origin, but we're shifted up 1. And so we're on the midway line here at 0, 1. So then sine normally goes upwards, but we have this negative in front, so that changes the direction that the sine value is going to be going. So instead of going up, we're going to be going down. We're going to hit our minimum value at 2. Or we're going to go back up, hit our midway line at 6. We're now going to hit our max, which is at 2. Come back down at 8 and hit the midway line. Okay, one period of what our graph looks like. So graphing the other trig functions, remember, can all be written in terms of sine and cosine. And so if it can be all written in terms of sine and cosine, we have to be careful because there's values where those trig functions are undefined. We can't have any value which sets our denominator equal to 0. It's not in our domain. Graphically, when you have a value which sets your denominator equal to 0 and not also your numerator, those are called, there's vertical asymptotes that occur there. We're going to now start getting in and graphing cosecant and secant. And that is part of 7.7 in this book. So recall, let's just do one of them. So let's just secant x, it doesn't matter which one we start with. This is equal to 1 over cosine of x. And so cosine of x cannot equal 0. And so if you again look at your unit circle and think about cosine is the x value of your point, and maybe this looks weird because we do have x here. It's the x value of your point. And so at the origin, or not, I'm sorry, 0 degrees or 0 radians, we have cosine is 1, x value. Here though, at pi halves, your x value is 0. And so it's undefined when x is pi halves. It's also undefined when you hit down here at 3 pi halves. But it's also any multiple of that, right? So basically every pi from these values, so really it's x equals pi halves a equals an integer. You can do that little contain sign in a set. And that funky z means integers. Basically, x cannot be these values. Those are the values where it's set this equal to 0. Let's do just a side note, just to recall, or something if you haven't learned this yet, you need to know this. I'm not going to go into detail. If you're in my college algebra class, this is and we're going to cover this week, is graphing rational functions. And so if you had some value, let's say p of x is some rational function of f of x over p of x, you have a vertical asymptote. Those occur when g of x is equal to 0. Not also f of x. That's the case, it's still undefined there, but it actually is an open circle on the graph and not an asymptote. So we actually have vertical asymptotes here. And I'm going to just call them VA for vertical asymptotes. When x, vertical lines are x equals pi halves. It's helpful to look at the domain and the range of secant. And we basically just bound that domain. When you're looking for domain, you're looking at any trouble spots, any values for x which would set the denominator equal to 0, and you exclude them. That's the only trouble spots we would have in here. We don't have any radicals. We don't have any logs. And so our domain are going to be all values except when x equals this. Or we could write this as set builder notation. See, this is a curly bracket, and then the variable that we're looking at, x, a vertical line which says such that x is a real number, but x cannot equal. Okay. The range is a little harder. So let's think about it again in terms of cosine. So if you think about the range of cosine, cosine, when we were graphing it, when we weren't, standing it up, normal cosine fell between -1 and 1. Okay, well, if we hit our smallest value of cosine, which is -1, 1 divided by -1 is -1. But then it hits all the values in between -1 and +1. Well, if you put in a fraction in there, and you just have 1 divided by 1/2, well, invert multiply, that's going to give us 2. 1 divided by 1/3, invert multiply, that gives us back 3. And so 1 over these fractions are going to give us numbers that are going to blow up. They're going to go to infinity. Those are the numbers that are fractions between 0 and 1, and then the numbers between -1 and 0, they're going to be going down to negative infinity. And so our range, we're going to hit all the y values from -infinity all the way to -1. And then we're going to hit all the y values from 1 to infinity. So when you're graphing the secant or cosecant function, if you can graph the reciprocal function, then you know where the asymptotes are. Wherever our cosine function is crossing the x-axis, that's where it's 0. We can't have 1 over 0. Those are where our asymptotes are going to hit. And then the other thing is where our maximum value is hitting for cosine. That is either going to be a max or a min for your cosecant function. And graphing. Y equals, let's say, a cosine b of x. Oh, sorry. Let's change that to secant. A times secant. B of x. First graph. Y equals 1 over a. Oh, sorry. Y equals, it's the same thing as 1 over a cosine of dx, but that's not what I want to graph. I want to graph a cosine. Okay, so when we wanted to graph y equals secant of x, not right, guys. We're just going to graph y equals cosine of x. Okay, so this one, we're not, the period hasn't changed. It's between 0 and 2 pi. So we have a pi half, splitting this into our pieces. Pi, 3 pi halves, and then 2 pi. Then we have negative pi half, negative pi, negative 3 pi halves, negative. So cosine, this one started at the max. It went down, it hit your x-axis, at pi, it hit the min, came back up at x-axis, 2 pi, the max. Going the other direction, negative pi half, hit the x-axis, negative pi, hit negative 1, up, and 2 pi, we're at 1. So let's make this dotted lines just because this is helping us, but it's not part of the graph. So once you've graphed this, then let's graph your vertical asymptotes. So, and again, these occur where your cosine graph is crossing the x-axis. So we're going to have one at negative 3 pi half here. It's going to be vertical lines. Really not shown on the graph, but they help you graph. Wherever it's crossing the x-axis, I'm right on vertical dotted lines. Basically, now you're going to go to your cosine or sine graph, depending on which function you're graphing, and you're going to make parabola shapes, either upwards or downwards, off of your cosine graph. And so wherever you have a maximum, you're going to have a parabola shape going upwards. So we're now graphing secant of x. So here at my max, well, that was when cosine was 1. So 1 over, secant is 1 over cosine, so 1 over 1 is 1. And then any value in between here, this is going to, so at pi, when cosine was -1, 1 over -1 is -1. We're going to have this downward shaping travel shape. Here, upward facing travel, downward facing travel, upward facing travel. So we now know what the graph of secant x looks like. We know what the domain is. We can't have cosine or the value equal to 0 in the denominator. We know what the domain and the range. The range we said was between negative infinity, -1, 1, and infinity. So what about the period? How long does it take for itself to start repeating itself?
I believe it's 2 pi.
Yeah, so you're right. So it's repeating itself every 2 pi. So we just look at this piece right here. Going up here, so we're waiting till it's going up again, right? And this is where it's going to start repeating itself. One full cycle of our period. Notice there's no amplitude for secant. So no amplitude. For trigonometric functions other than sine and cosine. So similarly, you can graph the cosecant function. This is the same thing as 1 over sine of x. So we have vertical asymptotes when sine of x equals 0. And so sine of x is equal to 0 on the x-axis. This is the y value of your unit circle. And so it's 0 at 0, pi, 2 pi, 3 pi. And so we have vertical asymptotes at x equals, let's say pi times k. 1 pi, 2 pi, 3 pi, 4 pi, and k is so our domain are all real numbers except for those. And our range, same kind of reasoning that I did with the secant, is 1 over the max of 1 is 1. So 1 over any number between 0 and 1 gives us, flipping it, number is going to infinity. So our range, same thing between -1 and 0. So you have negative infinity to -1, including -1, so a bracket, union, all the numbers from 1. So if we looked at this, period of sine of x, again, is 2 pi. So we have, draw your things, pi halves, pi, 3 pi halves, and 2 pi. So sine, first graph that one and do a dotted line. So sine of x starts at the origin, goes up to the max, the quarter point, halfway point, hits the x-axis, goes back down to the min. And then anywhere you have x-intercepts, that's where your graph is crossing. So those are vertical asymptotes of your secant function, cosecant function. And so now graph the throttle shapes off of that. So from there, basically, cosecant and secant are actually not that bad to graph. If you can graph the cosine or the sine version of that, secant or cosecant, then you can get the graph of the reciprocal trigonometric function really easily. Grab one.
Professor, can you go up a little bit? I'm not done copying.
Of course. So let's say y equals -3 secant of pi half times x. So first thing we want to do is graph the reciprocal function of the secant. And so the reciprocal function is, for secant, it's cosine. So we first want to graph y equals -3 cosine. And so looking at this, we can see what our amplitude is. Absolute value of -3 is 3. So that gives us a max. We're not shifting up or down. So max of 3, a min of -3. And then looking at our period. So that sandwiching pi half x between 0 and 2 pi, solving for x. Let's multiply everything through by the reciprocal of pi half. So if we clear that and make that 1x. Multiply b by 2 over pi. 0 times anything is 0 is less than or equal to x is less than or equal to. So notice here our pi's cancel. And then we're left with 2 times 2, which is 4. So start of one cycle is 0. End is 4. So halfway value would be 2, which means our quarter value is 1, and our 3/4 value is 3. So plot on the y-axis up to your maximum, down to your minimum, and then plot your special values. So 0, 1, 2, 3. Okay, so we're graphing cosine. Cosine starts either at the max or the min. Our value, though, is negative in front of the number in front of the trig, so it's going to start at the minimum. We're going to do dotted line because we're not really graphing cosine. We're trying to graph secant, and so this is just helping us graph this. So we're going to start at the min, hit our x-axis at 1, at 2, we're going to hit our max, back at 3, we're going to hit our x-axis, 4, we're going to hit our min and negative 3, 5, but back up to the x-axis, 6, max, 7, x-axis. Negative 1, x-axis, negative 2, a max of 3, negative 3, x-axis, negative 4, min of negative 3, negative 5, x-axis. We're going to make a dotted line.
Can you scroll down a little bit, please?
And then from our X-intercepts, so those are where the vertical asymptotes are for our function. Vertical lines there too. Across the x-axis. And based off of that, we can never cross vertical asymptotes where the function is undefined. And so you're basically going off your max and mins of the cosine function and doing your parabola shapes off of that. So it might ask you the domain and range of this. And from this, we can tell that our domain are all real numbers, but except when x is equal to or x cannot be, well, 1 is there, it's crossing the x-axis at 3. So we need to know how to express this. 5, 7, how can we express odd numbers? Well, 2 times an integer is even. So 2 times k will give me an even number. Well, also 1 gives me an odd. And the range, well, we're hitting all of our y values from negative infinity all the way up to y equals negative 3. Including negative 3, so put a bracket, union, and then we're hitting all the y values starting when x is positive 3. So you'll get some more practice with graphing the secant and cosecant when we look at the phase shifts. So we haven't looked at, we've graphed with shifts in our trigonometric functions, but we haven't looked at them shifting horizontally. We've looked at them shifting vertically, stretching them, shrinking them, but not horizontally. And so that's what we're going to look at after we come back from the break.
So we are looking at continuing to look at graphing trigonometric functions. And so let's actually finish the 7.7 and graph cotangent and tangent. Similar to cosecant and secant, these can be rewritten in terms of sine and cosine. And so y equals tangent of x. This is equal to sine of x all over cosine of x. So we're going to have values where it's undefined. Cosine of x can never equal 0. And so the values where it's equal to 0 is where you're going to have vertical asymptotes for tangent of x. So we're going to have vertical asymptotes at x equals, well, cosine is 0 at pi halves, 3 pi halves, 5 pi halves. And so those are values of, there's a couple ways that we could write it. I was writing it as pi halves plus pi k. But another way to write this, notice that it was always a odd, so 2 pi, let's do it this way, 2k plus 1 is an odd number times pi.
Professor,
Yes,
is that an x after the pi over 2 plus pi?
this is a k here and a k here.
Oh, okay. Thank you.
Yep. And k is equal to an integer. And so the values where sine of x is equal to 0, so when you have a numerator equal to 0 over another number other than 0, that's 0. And so we have x-intercepts. Occur when sine of x is equal to 0. And so sine of x equals 0. That was at x equals 0, pi, 2 pi. So the x-axis. And so we can write this as pi times k. Again, k is an integer. So when you're graphing these, it's kind of helpful, let's see, to graph these vertical asymptotes. And so we know it's occurring at pi halves. So I'm going to put a little dotted vertical line here. And I'm going to put a little midway point in between each one of these. And so 3 pi halves. Pi halves. Okay. Okay, so we said that they're going to have x-intercepts at 0, pi, 2 pi, 3 pi, negative pi, so when sine and cosine are the same, that's at pi fourths, 3 pi fourths, 5 pi fourths, 7 pi fourths. Well, not exactly the same. They're either equal to 1 or negative 1 at those values. Tangent's going to be. And so that's going to be helpful for us to graph. And so this is why I put kind of this halfway point here. And so let's think about it. At pi fourths, sine of pi fourths and cosine of pi fourths are both root 2 over 2. And so this is going to give us a value of 1. But at negative pi fourths, that hits down into the fourth quadrant, if we think about it that way. And cosine is positive in the fourth quadrant, but sine is negative. And so we're going to get negative 1 for tangent at negative pi fourths. And so you have this shape in here because of these asymptotes, where it has to have the asymptotes as x is getting closer and closer to those. We have this type of shape in between each asymptote. And I might have not done a very good, this is not to scale because this is going to look like this. So I did it too wide for the first one compared to the other ones. But you get a graph that looks similar to this. And so basically the number in front of tangent is just going to either going to make it stretch faster. And so that coefficient A, that number in front of there is bigger than 1, then it's going to grow at a faster rate. Where if that number is between 0 and 1, it's a fraction, it's going to elongate it. Same sort of idea with inside here. This is going to, the argument, if we multiply that argument, that value by some number, it's going to either stretch it or shrink it, the period. Looking at the period for tangent though, notice that it's repeating itself. So we can think of one cycle of a period starting at negative pi halves and then stopping at pi halves. Notice it looks like the same image again, starting from negative pi halves to 3 pi halves. And so the period for tangent is just pi. The domain, we found that when we found the vertical asymptotes, it's going to be all real numbers except when x is, what do we say? It's an odd number, so 2k plus 1 all times pi all over 2. And then our range, those are all the y values you're hitting on the graph. You're hitting all the y values from negative infinity to infinity. There's no jump in the graph on our y values. So you can say all real numbers or negative infinity to infinity. And there's no amplitude. Okay. So let's look at one with some transformations to it. about y is equal to tangent of 1/4 x plus 1. Okay, so we want to find our asymptotes. We want to find our period for this function. And that +1 out there is telling us that we're shifting that tangent, original tangent of 1/4 x, up 1 unit. So we can find our period by sandwiching this between 0 and pi. Actually, let's not do it between 0 and pi. And this one kind of makes sense maybe more next or later when we're graphing inverse functions. But let's label this. Notice that one full cycle here, it started at -pi/2 to pi/2. So that might be helpful for us to do. So let's look at the period between -pi/2. And I'm not going to include it because that's an asymptote. And this is going to be 1/4 x is less than pi/2. So let's look at this and multiply everything through by 4. So distributing 4, well, 2 goes into 4 twice, so this gives me -2 pi is less than x is less than 2 pi. So the period has just grown. So it's not as, it's bigger than what it was before. So our period is now between -2 pi and +2 pi. So the period for our new function y equals 1/4 x plus 1. I forgot the tangent in there. Tangent 1/4 x plus 1 is 4 pi. And so if you couldn't see that by just looking at that, you can take the largest value of the period minus the smallest. So 2 pi minus a -2 pi is 2 pi plus 2 pi is 4 pi. And then asymptotes. Well, this occurs when 1/4 x is equal to 2k plus 1 pi all over 2. So solve for x. And so if you multiply both sides by 4 to clear the fraction, that is when x is equal to, well, 2 goes into this 4 twice. I don't know if that was the best way to do it or not. And I can just distribute my 2. So this is going to give me 4k plus 2 all times pi. Well, let's just find a couple of these. So if k was 0, if I plug in 0 as an integer, this gives me 4 times 0 is 0 plus 2. So this is 2 pi. So we're going to have one when x equals 0, we had x equals 2 pi. So this is an asymptote. If I plugged in 1 here, so 4 times 1, k equals 1. This would give me x equals 4 plus 2, 6 pi. If I put in k equals 2, that's going to give me 10 pi. X equals 10 pi. Let's look at a couple negative numbers. So k equals -1. -1 is an integer. So -4 plus 2 is -2. So -2 pi. Plug in -2. We get 4 times -2 is -8. -8 plus 2 is -6 pi. And then let's look at the intercepts, or actually maybe just graphing that might just be helpful. Okay, so we have everything from -2 pi to 2 pi, sorry. So k equals 0. These were our asymptotes. So we said asymptotes here. And then let's look at intercepts. Well, normally our intercepts, right, was at 0, 0. The thing is that we're shifting things up 1 unit. So let's just assume or pretend that's like our x-intercept, shifting this up 1 unit. So this shifts it up 1 unit. So let's put this dotted line here. So this would have been like it was the x-axis if we hadn't shifted it up 1 unit. Okay, so normally tangent of x is starting at the origin 0, 0, but because that shift up, it's going to be here. So in between this pi, this is where they're going to be equal to each other, sine and cosine. And so normally they would have been at 1. Because we shifted up everything, this is now going to be at 2. This negative pi halves is now going to be down here because it normally was at -1, but we shifted up 1, so there. So we get the general shape of the tangent function. So you kind of use important points just like we do for sine and cosine, secant and cosecant when we're graphing these. So cotangent of x is almost identical to tangent of x, but instead of these are strictly increasing functions, cotangent of x is actually strictly decreasing. Well, cotangent again, this could be rewritten in terms of sine and cosine. Cotangent is cosine x over sine of x. We got vertical asymptote when sine of x equals 0. And so sine of x is equal to 0 on when x is on the x-axis. So 0, pi, 2 pi, 3 pi. So this is going to be pi times k, k an integer. So you have x-intercepts. That is when cosine of x is equal to 0. And so that's equal to pi halves, 3 pi halves, 5 pi halves, or 2 pi. Those are odd numbers. What did I do? No, it's 2k plus 1 times pi. All over 2. Okay, so we have asymptotes. Again, x equals 0, x equals pi, x equals 2 pi. So halfway point between 0 and pi is pi halves. Halfway point here is 3 pi halves. These are the values we said that it's crossing the x-axis. So negative pi halves is crossing the x-axis. So let's think about a couple numbers. So pi force. If we look at cosine of pi force, that's root 2 over 2. Sine of pi force is root 2 over 2. So that's going to give us back cosine, or cotangent is going to be 1 here. Where if we looked at, what is it? 3 pi force, sorry. Think about it. 3 pi force, cosine is negative at 3 pi force, but sine is positive. And so that would give us back a negative 1 here. So general shape, just like the tangent, but notice this is decreasing. And our asymptotes are shifted, pi half units. So our range is like tangent. It's negative infinity to infinity. But the domain, we have to be careful. We can't have any values where our vertical asymptotes are. So x is contained in the real numbers, but x, another way to write this, x cannot equal 2k plus 1. Nope, wasn't that one. This one was just pi k.
How do we know what our x-intercepts were? We're at the pi over 2 and 3 pi over 2. How do we find that?
We know x-intercepts are going to occur when our numerator is equal to 0. Because if we have 0 over a number, we're going to get back 0. And so I'm looking at when is cosine of x equal to 0? And I know that that's at the pi halves, the 3 pi halves, wherever I'm going to hit if I'm thinking of the unit circle, whenever I'm hitting the y-axis. 5 pi halves.
Oh, got it. Okay, I see.
Okay. Okay, so 7.8 pretty much is the same thing, except now, like I said, we were going to add in some horizontal shifts to this. So recall, hopefully you've seen this before, but if you add, let's say k is a positive number, I guess I could have just said greater than 0. Then this, if you're adding a number with your x, then that's going to shift. This shifts f of x, and it's actually the opposite direction than you would think. So this shifts f of x to the, if it's positive, to the left k units. So if we had minus k, f of x minus k, this shifts f of x to the right k units. And so we want to graph y equals, they kind of use different letters than I do, so hopefully I don't throw you off. Y equals a times sine, our argument, so parentheses b times x plus c, outside, and then plus d. Let's just look at it and do one. I'm just going to say the same thing, cosine here. We're going to look at those two, bx plus c plus d. So let's say it said graph y equals -3 sine of -2x plus pi halves. So we're going to do this pretty much the same way we were doing sine and cosine before. And so looking at the amplitude, we can tell that the amplitude is the absolute value of the coefficient in front of the sine. So amplitude is equal to the absolute value of -3, which is 3. Notice there's no plus or minus outside of this sine function. And so we are not shifting this vertically. And so we can tell right away that our max value is going to be when y is 3. So max is 3. And our min value, because of that amplitude, is -3. So we can find out what our period is and what our phase shift is by doing what we were just doing before, sandwiching our argument in between the period. And so our argument, we're going to sandwich between 0 and 2 pi for sine. So we have 0 is less than or equal to -2x plus pi halves plus is less than or equal to 2 pi. So just like we did before, we're going to isolate x inside of this compound inequality. And so first we need to get rid of that plus pi halves. And so we can undo that by subtracting pi halves to all sides. And so we get negative pi halves is less than or equal to -2x is less than or equal to, I need a common denominator. So this is really 4 pi halves minus 1 pi halves. So that's a 3 pi halves. So now I need to get rid of this negative in front of my x. We need to be careful because we're going to be multiplying or dividing by a negative, which flips your inequality signs. Let's think of this as multiplying by -1/2. That way I don't have to deal with fractions over fractions. So multiplying this through, 2's cancel. I have a negative times a negative, so this is going to be positive pi is greater than or equal to x, which is going to be greater than or equal to 2's cancel, and a negative times a positive is a negative, -3 pi. So I'm going to rewrite this as smaller to larger. Just make sure that the inequalities are facing the correct direction. So this is the same thing as -3 pi is less than or equal to x is less than or equal to pi. So my period, I can figure out the length of the period by looking at the largest n value, which is pi, minus the smallest n value of my period, in this case, -3 pi for one cycle. Well, that's a length of 4 pi. The thing is, we're not starting at 0 anymore because of it's called the phase shift for trigonometric functions when you're going left or right. And so the phase shift, we're no longer starting at 0, 0, we're starting at -3 pi. So the start value is -3 pi. We saw that the n value was pi. So halfway between pi and -3 pi. And so remember, that was where we were taking the larger value minus the smaller value. No, we were summing them.
Excuse me, I had a question.
Yeah.
So how did you get pi is greater or equal to x is greater or equal to -3 pi? Wouldn't the pi or -pi/2 times -1/2 would be pi/4?
Yay. Thank you, thank you, thank you, thank you. Yeah, I'm canceling and I shouldn't be canceling on the other two sides. So you're right. So those 2's don't cancel. I'm multiplying straight across. This should have been pi fourths. This should have been -3 pi fourths. Thank you for stopping me before I got further. So that definitely changes things. Come on. Okay, so our period, largest value is pi fourths minus the smallest value, which is -3 pi fourths. So minus a negative is plus. So a 1 pi fourths plus 3 pi fourths is 4 pi fourths, which is pi. So our start value is -3 pi fourths. I'm going to need more room. And my n value is pi fourths. So the halfway mark, well, it's the midpoint. And so the midpoint, we divide by 2 or multiply by 1/2. I'm dealing with fractions, so multiplying by 1/2 is easier. We sum pi fourths plus -3 pi fourths minus 3 pi fourths. And so here we have 1 pi force minus 3 pi force. That's a negative 2 pi force. So 1/2 times negative 2 pi force. And this is going to give me negative pi force. Okay, so the halfway mark between negative 3 pi force and negative pi force is really our quarter mark. And so that's going to be 1/2 times negative pi force plus negative 3 pi force. So that is negative 4 pi force times 1/2. Which is negative pi halves. I'm going to keep it as negative 2 pi force, just so all my denominators have the 4 in it. And then the 3/4 mark, take 1/2 times pi force, the larger value, plus the smaller value, negative pi force. Well, that's 0, and 1/2 times 0 is 0. Okay, so we got our important marks. So putting in those marks for one period, our amplitude was 3. And so up 3 and down 3. We're graphing a sine function. Sine normally starts at the origin. We're not shifting up or down, so we're going to start at the origin. So start point of one cycle, negative 3 pi force. We normally hit our max at the next value, but it's negative 3, so we're going to go downwards instead. And so we're going to hit our min, negative 3 at negative 2 pi force, back up to the x-axis, hitting the max, x equals 0, and then at pi force back down to the x-axis. And so here is one cycle or one period of y equals negative 3 times sine of negative 2x plus pi halves. Okay, so we got through one of those. I'll do a couple more examples of those tomorrow, but then we're going to get into the inverse trigonometric functions, which are helpful to help us solve for variables sometimes. And so if you don't remember how to do inverse functions, you might, or some, I'll go over a little bit, but not too much of that.